So, till now we have discussed constant random variable and Bernoulli random variable, binomial random variable or binomial distribution. Now we are moving into fourth one, that is geometric distribution. This is also common discrete type distribution. Whenever a random variable which is a discrete type random variable whose probability mass function is of the form probability of x takes a value small x, that is 1 minus p power x minus 1 times p, where x takes a value 1, 2 and so on. Otherwise, it is 0, then we call this random variable x is a geometric distributed random variable. Here also the p lies between 0 to 1. There is a connection between Bernoulli distribution with the geometric distribution. That connection is whenever you have a Bernoulli trials, the occurrence of the first trial in which you get the success, that follows a geometric distribution. Suppose you have a random experiment with infinitely many Bernoulli trials in it, and each Bernoulli trial has a random variable which is a Bernoulli distributed random variable with the probability of success p. This capital X is nothing but the trial in which you are getting the first success. That probability is you are not getting the success x minus 1 times, and the xth trial you are getting the first success. Therefore, it is 1 minus p power x minus 1 into p. All are consecutive and all the Bernoulli trials are independent. So, whenever you have a n independent or sequence of independent Bernoulli trials, the first success in the nth trial, that becomes the geometric distribution. So, the difference between Bernoulli, binomial and geometric, the Bernoulli distribution has only 2 jumps, the CDF has only 2 jumps, and the binomial distribution has only n plus 1 jumps. The geometric distribution has a countably infinite jumps. So, this is also discrete type random variable. So, let us discuss the CDF and the probability mass function of this random variable geometrically distributed. So, it has the jump points 1, 2 and so on. Therefore, at till x is equal to 1, it has the value 0. At x is equal to 1, it has a first jump. At x is equal to 2, it has a second jump and so on. At infinity, it touches 1. At infinity, it touches 1. So, that means the CDF has a countably infinite jumps with the jump points 1, 2 and so on, and the jump values are 1 minus p power x minus 1 into p. And if you draw the probability mass function, at x is equal to 1, it has some height. At x is equal to 2, it has some other height and so on. Then it will be keep decreasing. Then it will end up at a countably infinite points. If you add all the heights, that is going to be 1. So, this is a probability mass function and this is the CDF of the geometric distribution. The way I have explained through the data, suppose you have a data with the cumulative distribution, it is keep increasing at a countably infinite number of points, land up to be some finite value, or the probability or the histogram of the data that has some heights keep increasing and going down, and it has a countably infinite points in which it has these values, then you can conclude the data could follow the geometric distribution. So, in the statistics we get this type of graphs first from the data. In the probability theory course we started with the probability mass function, then the CDF and so on. In a theoretical way we study, whereas in the statistics we start from the data, then we conclude what could be the distribution of those data. So, one can discuss the mean, variance and the MGF for this geometric distribution also. So, the mean for geometric distribution is going to be 1 divided by p, and the variance of geometric distribution is going to be 1 minus p divided by p square, and one can get MGF of geometric distribution, that is p times e power t divided by 1 minus p times e power t. So, in notation we use x follows geometric with the parameter p. When we say x tilde geo within bracket p, that means this is a geometric distribution with the parameter p, whose probability mass function is 1 minus p power x minus 1 into p, where x takes a value 1 and so on. You can always create another random variable in which the probability mass function start from 0 onwards instead of 1 onwards, then that random variable is called it as a modified geometric distribution. In the real world problem, sometimes you come across the possible values are 1, 2 and so on, or sometimes the values start from 0, 1, 2 and so on. So, you can use the correct probability mass function, so that summation is 1. I am not going for the derivation, the same derivation what we have done it for the binomial, you can use the same technique. Now, we will move into the fifth one, that is a negative binomial there is another name for this distribution, that is called a Pascal distribution. A discrete type random variable is said to be a negative binomial or a Pascal distribution whenever the probability mass function is of the form probability of x takes the value small x is x minus 1 c r minus 1 multiplied by p power r and 1 minus p power x minus r, where x takes the value r, r plus 1 and so on. Otherwise, it is 0. Here r is positive integer and p lies between 0 to 1. That means whenever you supply the value of r and p, you know the distribution of this random variable. We use a notation x follows a negative binomial NB with the parameters r comma p. This is also related to the Bernoulli distributed random variable in the form of capital X denotes in the x trial we are getting a first time orth success. It follows negative binomial whenever each trials are Bernoulli and they are independent. So, whenever you have a independent Bernoulli trials, obtaining first time orth success, that follows a negative binomial distribution with the probability of success is small p and the probability of failure is 1 minus p. When r is equal to 1, the same random variable x follows a geometric distribution with the parameter p. When the the rth success, that is when it is a first success in the xth trial, then that follows a geometric distribution. Therefore, geometric distribution is a special case of negative binomial or Pascal distribution with the parameter r is equal to 1. The probability mass function can be visualized once you are getting r minus 1 success out of x minus 1 Bernoulli trials. That follows a binomial distribution followed by the rth success. That means x minus 1 c r minus 1 p power r minus 1 1 minus p power x minus 1 minus r plus 1, that can be treated as r minus success getting out of x minus 1 trials, which follows a binomial distribution, multiplied by the rth success getting in the xth trial. Therefore, x can be r, that means you may get the rth success in the xth trial itself, or you may get rth success in r plus 1th trial, and so on. So, that is the interpretation of the probability mass function p of x equal to small x, where x takes the value r plus 1 and so on. So, this is also discrete type random variable, and the CDF has countably infinite jumps. So, I am not going to draw the CDF of a negative binomial, but one can visualize the CDF has a countably infinite jumps of this discrete type random variable. For this random variable also, one can find the mean, variance and so on. The mean of this random variable is nothing but r divided by p, and variance of this negative binomial, that is r times 1 minus p divided by p square. You can verify when you put r is equal to 1, it has to be a same as of geometric distribution, and the MGF of negative binomial or Pascal distribution is p times e power t divided by 1 minus p times e power t whole power r. When r is equal to 1, that is same as the MGF of geometric distribution. I am not going for the derivation, but one can derive and you can get the same answer. So, the next distribution is Poisson distribution. This is a very important distribution because this connects probability with the stochastic process in the different level. A discrete type random variable is said to be a Poisson distributed random variable if the probability mass function of this random variable is going to be of the form e power minus lambda, lambda power x divided by x factorial, where x takes a value 0, 1, 2 and so on, otherwise 0. Here the lambda has to be strictly greater than 0, it is a constant. So, whenever any discrete type random variable whose probability mass function of this form e power minus lambda, lambda power x by x factorial, where x takes a value 0, 1, 2 and so on, otherwise the probability mass function is 0, then that random variable is called it as a Poisson distributed random variable. You can verify this probability mass function, this is always greater or equal to 0, and if you make a summation over x starting from 0 to infinity, e power minus lambda is out and e power minus lambda is outside, then the summation, and that summation quantity becomes e power lambda, and since the lambda is strictly greater than 0, therefore this quantity is going to be 1. Therefore, this is a probability mass function. One can draw the CDF for this Poisson distributed. X takes the value 0, it has a jump. At x equal to 1, it has another jump. X equal to 2, it has another jump, and so on, countably infinite jumps. It touches 1 at infinity. Similarly, if you draw the probability mass function of a Poisson distribution, 0 it has some height, and 1 it has another height, 2 it may have another height, and so on, and it will be keep decreasing at countably infinite number of points. So, this is a one diagram in which the lambda value is so that it is keep increasing decreasing, or there is a possibility it may have a at x is equal to 0 it will have a tallest, then it may keep going down, and whatever the possibility, the summation of probability mass at a countably infinite number of points, it is going to be 1. So, the same conclusion, if the data has a cumulative distribution graph or the histogram look like this CDF form or probability mass function form, then one can conclude that data follows Poisson distribution. And there is another relation with Poisson distribution with binomial and Bernoulli. If you have a n independent Bernoulli distributed random variable, that summation becomes a binomial. When the n becomes very large and the p probability of success is very small, one can prove the limiting case of n tends to infinity and p is very small, then the binomial distribution will tends to Poisson distribution. For binomial distribution, the n is always a finite quantity and the p is the probability of success in any one Bernoulli trial, and all such Bernoulli trials are with the probability of success p is same and all are independent, therefore you are getting the binomial distribution. But for larger n, also when p is very small, then the limiting case of the binomial distribution goes to Poisson distribution. Therefore, you have a countably infinite jumps in the CDF. One can visualize the limiting case of a binomial distribution is Poisson distribution. So, that is the connection between Bernoulli distribution, binomial distribution and Poisson distribution. One can get the mean for Poisson distribution, that is nothing but summation x times probability of x is equal to x, where x takes a value 0 to infinity. This is nothing but x times probability of x equal to x is e power minus lambda, lambda power x by x factorial, when x takes a value 0 to infinity. X factorial and x cancel, so you will get x minus 1 factorial. You can take 1 lambda outside and the remaining quantity becomes 1. Therefore, the mean is going to be lambda. Similarly, one can find E of x square, that is nothing but summation x square times probability of x equal to x, where x takes a value 0 to infinity. The similar way one can compute, so you can get the answer, that is a lambda square plus lambda. If you do the little simplification by substituting probability of x equal to x, that is e power minus lambda, lambda power x by x factorial, do the simplification, you will get lambda square plus lambda. Therefore, you can get the variance of x, that is e of x square minus e of x the whole square, and expectation of x square is lambda square plus lambda, and e of x is lambda, therefore that is lambda square. So, simplify, you will get lambda. So, this is a very important result. The mean and variance of the random variable is same, which is lambda. So, here lambda is a parameter, because once you know the value of lambda, you are known with the distribution. Therefore, we use a notation x follows capital P with the parameter lambda. That means this is a Poisson distributed random variable with the parameter lambda. So, once you specify the value of lambda, you are known with the distribution of this random variable. So, in Poisson distribution, the important result is mean and variance are same, which is same as the parameter. Similarly, one can compute the moment generating function, because through this you can get all the moments of order n. So, if you do the MGF calculation, it is expectation of e power x times t, then that is same as summation e power small x t, and the probability of x takes a value small x, that is e power minus lambda, lambda power x by x factorial, where x takes a value from 0 to infinity. You can keep lambda and e power you can keep lambda power x and e power x t together. So, therefore, this is nothing but summation x is equal to 0 to infinity e power minus lambda, lambda times e power t power x by x factorial. So, if you do the little simplification, you can get the answer that is same as e power lambda times e t minus lambda, so that I can write it as minus 1. So, it is basically e power minus lambda is outside. So, this summation is nothing but e power lambda times e power t. Therefore, it is a exponential of lambda times e power t minus 1, that is a MGF. So, from the MGF you can always get the by derivative, you can get the expectation of x, expectation of x square, then through that you can get the variance also. So, since it is a discrete type random variable, you can go for probability generating function. So, even though I have not explained how to find out the probability generating function for all the distribution, so you can starting from the Bernoulli, binomial, geometric, Poisson and negative binomial, all these distribution, because it is a discrete type and it takes positive integer values, therefore, one can go for finding the probability generating function of these common standard discrete type distributions. The next one, that is number 7, that is a discrete uniform distribution. A discrete type random variable is said to be a discrete uniform distribution whenever the probability mass function is of the form probability of x takes a value small x, that takes a value 1 divided by n when x takes a value x1, x2 and so on xn, otherwise 0. Here the xi's are the real numbers. So, it can be any n points. The probability mass function at those n points is same, which is same as 1 divided by n, and all other points the probability mass function is 0. Such a discrete type random variable is called a discrete uniform distribution. Why the word uniform? Because the probability mass function is the same for all such n points. So, all such n points has to be distinct, all should be different, distinct n real values in which the probability mass function is same, and since it is a probability mass function, the summation has to be 1. Therefore, for a uniform distribution the probability mass function is 1 divided by n, then only the summation is going to be 1 and all are going to be greater than or equal to 0 only at those n points. So, such a discrete type random variable is called a discrete uniform distribution. Let me draw the sample CDF. Suppose x1 is here, x2 is here, x3 is here, xn is somewhere here. It need not be equidistant, it can be any n distinct n points. And the CDF, I have just list out x1 is the first value and x2 is a greater than value, x3 is a greater than x2 and so on. So, the CDF is 0 till x1. At x1 it has a jump and the jump value is 1 by n. So, this height is 1 by n. Till x2 the value is 1 by n. At x2 it has a next jump. Till x3 it is going to be the same value and this jump is 1 by n. And x3 it has the next jump and this jump is 1 by n. All the jump heights are same. At the point xn it has the last jump and it becomes 1. If you see the CDF for any discrete type random variable which has only n jumps and all the jump values are same, then that random variable is a discrete uniform distributed random variable. You can relate this CDF with the earlier random variable CDF. It may have a 1 jump or n plus 1 jumps or countably infinite jumps, but the jump values are different at a different point. Whereas here it is fixed always n jump points and always the n jump values are same, which value is 1 divided by n, that value is 1 by n, then that CDF is corresponding to the CDF of a discrete uniform distribution. So, if you draw the probability mass function at those n points, the heights are going to be 1 by n, same heights. That means if you have a data in which if you draw the histogram and all the histogram heights are same with the n number of points or the way you made a groups and so on, you can think of that could comes from the discrete uniform distribution. Or the data, if you draw the CDF cumulative distribution and it has the same jump heights and only finite number of jumps, then it is a discrete uniform distribution. That means we can interpret in a other way also. You have omega consists of finite or countably infinite or uncountably many samples in it. The way the mapping goes, it maps into x1, x2, xn such a way, partitioning omega into n pieces and each one has a mass 1 by n. Each one is attached with one point whose probability mass function is 1 by n. So, you partition, this is the first partition, second partition and so on. This is the nth partition whose mass is 1 by n. That means that random variable is discrete uniform distribution. Since it is a discrete uniform distribution, you can find the mean is nothing but summation x times the probability of x takes a value small x, where x takes a value from x is equal to x1 to xn, and the probability of x equal to x is 1 by n. Therefore, the 1 by n can be taken outside and you add all the values I is equal to 1 to n. So, the mean is nothing but mean or expectation is nothing but sum of those values multiplied by 1 by n. That is nothing but its average. So, whenever the random variable is of the discrete uniform, the mean or expectation which is same as the average. We can go for finding the variance of x, that is expectation of x square minus expectation of x the whole square. So, first you compute the expectation of x square, then you substitute in this formula, then you can get the variance. So, since the probability mass function at those points is 1 by n, therefore, this is going to be 1 divided by n summation I is equal to 1 to n x I square minus this is 1 by n summation of xi, I is running from 1 to n the whole square. So, if you do the simplification you can get it, and a similar way you can get the MGF also. The MGF is going to be MGF of x, that is same as 1 by n summation e power t times xi, where I is running from 1 to n. Because the probability of mass function at x equal to x is 1 by n, that can be taken out. So, the summation e power t times xi, I is equal to 1 to n, with the multiplication 1 by n will give the moment generating function for the discrete uniform distributed random variable. With this we are completing some common discrete distributions, starting from constant, Bernoulli, binomial, geometric, negative binomial, Poisson, and discrete uniform distributions. So, there are 7 distributions we have discussed. They are all called common discrete type random variable whose probability mass function and CDF, mean, variance, MGFs are discussed.